So we were checking out that delta of OJ with respect to delta net J. What was it? What was it? I just now explained it. By looking at the figure,
Resultant, ma'am.
By looking at the figure, if you can let me know. So delta from here to here I have to get. What will I get? The operation of it. I told you I'm going to use a sigmoid function over here, my activation function, and my reactivation is summation. So what will be my value of that?
Net J.
So it's going to be delta of what? Of what? Sigma of net J. Why sigma of net J? My sigmoid function is going to be applied onto the value where it receives all the summation of it, right? Because when I tell this, when I'm writing like this, which means that on my output, the sigmoid function that I do, if you remember, we did output is equal to sine function, that's a signum function of W into X, which means that it is performing this operation on the value, the final matrix value that it got, where it changed its value to -1 based on 18.9, 6.5, -1.5. If there is something like that, it changed its value to 1, 1, -1. So it is applying this onto these values. Where did I get these values? Which is nothing but the summation values. So I have these summation values value here. So I'm going to apply that with respect to net J. You're getting this point? Where did we get those values? So from here, if I have to get the activation function is this. If I have to apply the activation function, I have to get these input values, the pre-activation input values. So this is my activation function, which is applied on the pre-activation function, which is nothing but the summation divided by the whole values of it. So from here, if I start, okay, there's a derivation that is already there for this, for each and every perceptron. What will be the value of it when it is applied with the pre-activation and activation function? I'm going to write it directly for your reference over here. It is basically OJ into 1 minus of OJ. So this is the value of each and every neuron. Each and every neuron, whenever I consider each and every neuron value, okay, even though it has an activation function and a pre-activation function for that particular neuron, the final output of it will be just directly writing it as OJ minus 1 minus of OJ. That is the output of that particular neuron into 1 minus of that particular output value. Okay, so now what we did, we got this difference. We got this difference value and we got even this value, second operation value. So now entirely for my output neuron, I have got the value. Entire value for my output neuron, I have the value, and that value is going to be minus of Tj, okay, minus of Oj into. Where did I get this value from? Where did I get this value from? Minus Tj minus of Oj? The first operation that I performed.
The first calculation.
Yeah, with respect to delta Ed divided by delta Oj, right? From here
Yes.
to here, and now from here to here, this is the second operation. For the first operation, I know this is the value. For the second operation, it is Oj into 1 minus of OJ. So this entirely for one particular output neuron, this is my entire value calculation. So what I do when I'm coding, I will write this part, okay? I will write this part and make sure that each and every output neuron will have something like this created, okay? Along with the learning rate. Why learning rate? Because we have to know each and every step whatever we perform. So this basically is going to be my delta Wji is equal to entirely this term for my output neuron. The weight updates that I'm going to perform with my output neuron is going to be delta Wji is equal to minus the learning rate into Tj minus of Oj into Oj into 1 minus of Oj into Xji. Why is this Xji? Because it has to let us know to which particular input that we are going to consider. Because input values plays a vital role. To which particular input that I'm going to take out, it is going to be calculated like this. So now my final thing, with respect to my output neuron, when I have to update my weights, I'm going to use this formula called as Wji is equal to minus learning rate of this into Xi. This will be the actual coding part of it. Minus the learning rate into Tj minus of Oj into Oj minus 1 minus of Oj into Xi. So I will directly just write this as delta K. Because my output neuron, I normally represent it with K. I will just directly write this as delta K. So whenever I encounter something for output neurons, when I have to update the weights with the output neurons, I will just call this equation called as delta K and I will update the values. You got this? So I have done it only for the last part of it. Only for the output neurons I have done. Now I have to do it for the hidden neurons. What will I be updating the weights for the hidden neurons? I have got it for the output neurons with respect to the loss function. I got a value. Next, I will be doing ahead with the hidden neurons. Let's go ahead with the hidden neurons. I will finish this and I'll stop for the day. With respect to the hidden neurons, what is my diagram now going to be? I have my output neuron where I will get ED. Okay. So this is okay now because I've got the output value of it and I had an activation function and a pre-activation function called as summation. I represent it as by delta net K. Okay. So before this comes my hidden layer, right? Where do I get my hidden layer? Where do I get my hidden layer? In your perceptron model, where is your hidden layer? Multi-layer neural network?
Between input and output.
Yes. So here I have an input and an output. I have an output over here. So between that, which means my output layer, my hidden layer will come just before that. So I'm going to write something over here that even this layer has a pre-activation function and it has an activation function. So I will just write output of this particular will be Oj now. Output of my hidden neuron is Oj and my summation value is net J and the weight between these two is Wjk. Okay, is this diagram clear? Because based on this is what we will be deriving the hidden layer weights. Are you clear about this diagram now? So this is my output I already have done this calculation and it is ready for me. Now from here, I will be going ahead with the next, identifying the weights of the hidden neuron. It has an activation function, so it can be either ReLU, TANH or sigmoid, any of the activation function. And the output of that is OJ, but the summation of this is net J that I have represented. Clear with this? Okay, if we can go ahead now what I'll write, so I'm going to write it as delta ED, okay, divided by delta net J. Why delta net J? Because I want it from here to here, okay, is equal to, see, this will be same for any number of layers that you have. You can downstream it to the number of layers. So I'll write it as summation of K belongs to downstream of J. You can downstream it to any layers that you want, but they are hidden weights, that's it. N number of hidden layers that you get, N number of hidden layers that you get, you'll be applying the same thing, but you will be downstreaming one after the other. So how do I write it as? Delta of ED divided by delta net K, ED with net K, okay, first thing, into delta net K divided by delta net J, okay, delta net K divided by delta net J. So I have the two paths that I have written for my hidden layers. From ED, let me change the color for your identification, from ED to net K, from net K to net J. I want these partial derivatives. If I get these partial derivatives, I'm almost done. I can calculate my hidden weights also. So how do I do that? The values of this, normally ED with net K, what will be the value of it? From here to here we have calculated. What is it? We have already calculated ED with delta net K. What was the value of it? How much ever you remember? So it was
What, ma'am?
whatever you remember. We have already calculated this part. We have already finished till here. What was that
Yes,
value
ma'am.
that we got?
Total net J we got.
Total net J or delta ED divided by delta OJ into delta OJ divided by delta net J. We got some value when we performed this operation. What was that value? T minus of Tj minus of Oj, minus sign here, into Oj minus 1 minus Oj, right? Where I derive this as directly delta K. Remember this part now? We just did this. We just did this derivation here. This part. Remember that?
Yes, ma'am.
So from the output to this, so this is delta K. So I already know this value, which is equal to delta K minus delta K, okay? This minus is still there, so I'll take this as minus, so it's going to be minus delta K. So I have the value minus delta K and net K into net J. So I have to get it from here, from this value to this value. Now I have to calculate. So which basically normally is going to be into WJK into from here to here. Will that be correct? Am I right for that?
Yes, ma'am.
Because I just want from here to here. From here to here, the connection is only this and this operation. So it is WJK into delta of OJ into net J. I will just write directly like that. And we already know for one particular neuron what will be the value. There is a derivation already and I gave you one direct value of it. For one particular neuron which has a pre-activation and an activation function, the output of that particular neuron will be, let me guess if you are able to guess it correctly. I just now told, if I have to really get an output of one particular neuron where it has a pre-activation and an activation function, the output of that neuron will be, come on, it is so easy. What is this? What is this? The one that I have circled in purple color, what is that? Am I not representing the same? This is also delta OJ into delta net J. This is also OJ with respect to net J. What will be the value of this particular neuron be? Is it difficult even now? How did we get this value? For this, when I was solving this, then I told that for one particular neuron, this was the neuron when I took it in the previous case, it has a pre-activation, it has an activation, okay? For the output of this particular neuron will be OJ into 1 minus of OJ, right? Now again, I have the same neuron over here. This is my same neuron which has a summation, which has a reactivation and an activation. So the output of this J, what will it be now? What will it be now? Guys, I've already told you the same answer here. I did it for this and I know that the value of that neuron is this. Again, I'm doing for this. What will be the value of this neuron? What will be the value of this neuron be? Right? So if I have a phone in my hand and I know the output of the phone, it performs so and so. It performs, it has a WhatsApp feature, it has a dual camera, it has this is the output of that feature. So I know the output of that phone is so. Now I'm changing that phone to the other person. Does the output of that phone change?
No, ma'am.
It remains the same, right? It's a similar way. I'm telling here, this particular neuron, when it has a summation function, when it has a activation and pre-activation, the output of that particular neuron is basically going to be OJ into 1 minus of OJ. Now the similar is shifted. I have the same output. I have a summation that I am doing. I have a pre-activation and the activation that I'm going to do. So output of that neuron will remain the same, which is OJ and the thing. So I'm going to write it directly this as delta K into WJK into OJ into 1 minus of OJ. Okay. So this finally will become my output of the hidden neuron. So I'll have just the remaining terms. What I'll do is I'll just take all the terms which is, so delta, that is Oj into 1 minus of Oj. I'll write this summation over here because these are all the dependent terms. Summation of, okay, with respect to downstream of J, which is into delta K into delta Kj. So this is going to be my training rule for the hidden neural network weights or the hidden unit weights. So this is the previous one. This is the training rule of the output weights. This is the training rule of the hidden weights. So by using this, we will be calculating the backpropagation algorithm because it's the same thing. I got it for one output, I got to know this value, I got it for this. I have only one more connection to this where I know the weights of this and I know this is the same neuron. For the same neuron, whatever operations it performs. Again, I'll go back one track. I will get to know the weights of this. So when only the you can see only the weights are updating. This remains the same. This is what I've got it using delta K. This complete operation of this is delta K. Okay, delta K into WKI, which is WKI is this value into OJ. The output of this is basically OJ into 1 minus of OJ. Okay, so if I have one more previous neuron before this, so I'll be having something called as again WJK1 or something. Okay, let me just consider that. So and the output neuron of this again will be something, right? So I'll be downstreaming it with the same J values, the number of, you get it, you just downstream that. And basically, finally, I will get my X value of that. But X value, I've already taken it over here into XJI. So I need not consider it. So I already have that X input instances that I've considered in my final calculation itself. So previous to that, I'll be doing it only by using this training rule of weights, hidden weights. So I have the hidden weights done here. I have the output weights. Apart from that, I don't have anything changing because I've considered the input with respect to my output itself. So everything is done, complete. My neural network structure itself is done. When I have a neural network structure like this, something, let me just take the neural network structure like, I have 1, 2 and 3. I have 2 outputs, okay, and finally I get the loss function of it. Okay, let me just consider like this. I have one more hidden layer over here, and I have the input neurons. Okay, so these are my inputs, these are my H1s, these are my H2s, these are my outputs, and this is my loss function. If I have something like this, you can understand that I can calculate this output of one particular neuron using this equation. Why? Because it corresponds to all its input weights. So you can just omit this. It corresponds to all its input weights x1, x2, x3 because it has xij here. So it will consider the input weights of that. Okay. So I've got this particular part is done. And now the next part is I have to calculate this. If I have to calculate each and every neuron in that, I'll apply this. I'll be only changing the J value of this from I to 100, 1 to 100, first neuron, second neuron, third neuron, fourth neuron. I'll apply this training rule on that. Okay, because this is the only weights that I'll have. I have the weights over here and I have the delta K value of it. The delta K value of it is also known, and this is OJ minus of 1 minus of OJ, where I'll get this value also. So I will get the first layer is done. Again, for the second, I can do it. For the third neuron, I can do it. If I have to previously go one step ahead, I have to get to know only the weights of this. The weights of this I will get to know, and I already know this particular value of it. This particular value of it is OJ minus of TJ. Okay. So I've got this to know, and the value of this is this. Okay, I know the weights of this. The weights of this is also there. Okay, and I again I know this weight, and this entirely is my delta K, which is my delta K. So till here I have encountered. Now again I have to just go back to one single step, and I get these weights done, and I already have these inputs for that. So entirely I have backtracked my algorithm completely. Is this clear? Do you have any doubts here? Any doubts in this? You're completely clear?